Hi, my name's Doug. Welcome to the live stream tonight. It is April 14th as we make this live stream, and we're glad you're here. Welcome to Emerald Hill Skies. We're broadcasting from the outskirts of Louisville, Kentucky, in a 61-acre campus called Emerald Hills, so it's fitting that we should call the observatory Emerald Hill Skies. If you'd like to see what the observatory looks like, just briefly, this is what it looks like during the daytime. You can see the telescope just scooting its head up above the wall of the observatory there. And you might wonder what the scope looks like. Here's a live view of the scope. This is actually right now. It's out there. It's a RASA 11. It's sitting on top of an iOptron CEM70G mount, which is mounted to a PureTech adjustable height pier. And that pier is in a PureTech Telestation 2 observatory. It's a beautiful night tonight. The sky is clear, but look at that big searchlight that's beaming down at us out of the sky. That is a sun-looking moon. It's actually the moon, but it looks like the sun, doesn't it? But we're going to see what we can see anyway. Let's get over to our actual camera view. This is our first object of the night, Caldwell 53. And let's do a plate solve here to make sure, once again, that we're tuned in to exactly where we should be. Again, if you've been with us before, you know that plate solving is when we compare the expectation of the scope with what's really being seen through the camera, looking through the scope. I'm going to just check our audio to make sure that our audio is working here. Yep, there we are. Just like to make sure that the audio is really real. And there's Rowan already here. Rowan, thanks for checking there with us. You've given us a couple of thumbs up to let us know things are working. If you don't mind, let us know where you're viewing from. So we're synced and we're within 1/100th of a degree of the right place. So we're going to start live stacking. And we do that with this little sequence. It just says start imaging. And what this will let us do is start zeroing in and stacking subframes on top of one another. I'm going to make sure that you're seeing what I think you are. Yeah, these subframes, this is called live stacking. When these subframes stack on top of each other, you see the first frame, and it'll pop in just any second now. See if it comes in right around now. And the first thing we have to do is try to color balance our screen. We use this little set of bars down here in the lower right-hand corner. And then the next thing we do is we try to start adjusting these vertical bars at the bottom with what's called this live histogram. And if you've worked with photography at all, you know that a histogram is basically a reading of the different colors compared to their available light. And what we'll do now is we'll zoom in on this object. Again, this is Caldwell 53, and as you can see, it is a galaxy that is what's called an elliptical galaxy. Now, I know it looks a little bit like a spiral galaxy, but it's really an elliptical, and what an elliptical means is that it doesn't have that spiral arm windmill kind of shape as much. And the difference isn't that pronounced with a galaxy like this because it already looks pretty much like a spiral. But what this means is that the closer we get to it, the less of that spiral structure we're able to detect. Rowan, we see that you're on here from Australia. Wow, that's awesome. Dennis, welcome back from Northern Colorado. We're glad to have you as well. Man, all the time you guys stop in, it really makes a difference because it's a little less lonely. Now, I'm operating inside my office. This is where I work during the day here at Emerald Hills. And it makes it kind of nice because no matter what the environment, I can be inside the office here in shirt sleeve temperatures. It's 72 in here in the office. And outside, it looks like when I look over here at this little Pocket Power Box Micro software panel, it looks like it's just 48 degrees outside. Now, that's not so bad. But it is a 46% relative humidity, which is getting up there. It'll be a little bit damp. And at 48 degrees, I'm sure I'd need to have a coat on. And after a while, it kind of feels sort of clammy out there, I'm sure. But in here, it feels nice and comfortable. So we're operating about 200 feet from the observatory. And this lets us operate all temperatures, all times of the year. So we're glad you're here joining us. This Caldwell 53 is a bit of a beautiful sight, isn't it? It is NGC 3115, a lenticular elliptical galaxy in sextans, sometimes known as the Spindle Galaxy. It's about 30 million light years from our location, and you can see that in a regular telescope it would be rather small, but here in our electronically-assisted astronomy screen, we hope that you can see it a little bit better than you would if you were looking at it through an eyepiece, especially on such a brightly moonlit night. It has a supermassive black hole in the middle, and we don't detect a lot from its nucleus, even though it has that big black hole in the middle. All right, we're going to snap a picture of this to save it exactly as we've seen it tonight. And this is our view of Caldwell 53. Now, let's go to Caldwell 53 here in our planetarium software again, and let's bring up our sessions and start a new session tonight. And let's call it Caldwell Part 3. We'll call it 2022-04-14. And I'm going to set our sign-off time quite a bit into the future here. I don't know how late I'll stay tonight, but we'll get this session going. I'm going to make a note here in the comments, bright moon. I don't know what percentage the moon is, but let's take a quick gander here and see if we can see what percentage illumination we're getting from the moon tonight. Maybe you guys can help me look this up. 94% it looks like. That's really pretty bright. That's almost, I might as well say almost a full moon tonight. 94%. And that will affect some of these targets for sure. Okay, I'm gonna save that as a session that's going live. And then in this entry, by the way, it looks like we looked at this Caldwell 53 almost a year ago this exact night. Look at that, April 15th. And boy, it looks like we were dropping frames. So it must have been a misty night when that happened. We're going to add a log entry here. We're going to set our observing list on our Caldwell list. We're going to put it on the real Caldwell list because that's kind of what we're observing from. And notice it's already picked up Caldwell Part 3 as the observing session here. So it's really doing a good job picking that up. I'm just going to tell it that we're using the RASA 11 with the 2600 camera. And then in the notes, I'm going to say, wow, this was a fine looking elliptical spindle shaped galaxy. You know what a spindle is? It's in a weaving, right? In a weaving, the spindle does something with I don't know how to describe it, yarn or something, whatever you use to make rugs or whatever. That's what a spindle does. So take one last look at our live view, and now we'll, our stacked view. We'll go back to our snapshot view that we call next target. And that's just going to prepare the screen, go back to our 3-second exposures at 400 gain so we can go get our next target. Let's come back here and in our working list now, what we do is we take the full Caldwell list and we export it into a working list. And then we sort it by the height above the horizon. And you can see Caldwell 53 was at 44 degrees. So we're all done with that. We'll put a checkbox there. And then what we'll do is we'll right click and we'll say add that to the observing list called Caldwell Observed. And then what we do in our live sky bridge portal, which lets us see between planetarium software, Starry Night Pro, and also we can use it to look at Sky Safari, which is another software you use on our app. Hello, Ernie. Glad to have you here from Buffalo. if you don't mind, I see several others are logged on. Let us know where you're watching from. I'm going to go here to the observing list. I'm going to go to Caldwell Working. Now that we've transferred it to our observed list, I'm going to search for 53 and, whoops, I got to say edit first. Now I'm going to search for 53 and I'm going to remove it from this working list. And that's what we do. We move objects from the working list to the observed list. So the working list gets smaller and smaller. The observed list gets bigger and bigger. And that way we can tell what other objects we have left in our list. So we'll just leave that open and work from that throughout the night. So we're done with 53. Hey, look what's next. Caldwell 1. So we've stopped our live stacking process in our imaging software. We use SharpCap Pro. We're gonna now center on this object, Caldwell 1, and then we're gonna slew to it. And as we do that, we'll put you at the scope so you can watch the telescope move and head to that next object. You know, the RASA 11 is 11-inch aperture. 11-inch aperture. Funny thing about the RASA is it doesn't really have a classical eyepiece. So if you were to come here to Emerald Hills and try to look through the telescope with me, you would still be looking through this same camera that we're all using tonight. You can see that little red ZWO ASI2600MC Pro that's mounted on the front of that corrector plate at the front of our RASA. So we're all using the very same eyepiece. And I'm using the word eyepiece kind of figuratively, aren't I? There's that sky again. You can see we're pointed at a part of the sky where the moon is not quite as bright. And that's a good thing. So let's go back to our screen and let's look at our planetarium software here and kind of get a picture of where we are. You can see here, this is the Little Dipper, and there's Polaris, the North Star. So as we zoom in, we're just a little bit below the North Star. And below us is the constellation Cepheus. So it always reminds me of a house. And then down here is Cassiopeia. And if you can just think about between Cassiopeia and the North Star or the Little Dipper, that's where we're headed to be able to see Caldwell 1. As we zoom in here, you can also see a red rectangle, and that is an approximation of our field of view on our RASA telescope. So you can see this is a very small object, but what is the object? Well, it's this open cluster in the middle. And when Sir Patrick, actually it's not just Sir Patrick Moore, that's the name he used when he was around town, but when he signed his name, he would sign it Sir Patrick Caldwell Moore. It was a compound last name. So he called his list the Caldwell List. And the first object he chose on his list was Caldwell 1, this open cluster. So let's go back to our imaging software. And while we're here at the 3-second exposures, let's go back out to an auto screen and let's do a plate solve. And this will help us make sure we're aimed at exactly the right place. And for the first 2 or 3 objects of the night, it really helps to do a plate solve because the mount is still synchronizing with what the camera is expecting to see. And every time we plate solve, that's kind of a vernacular name for trying to find where we are in the sky. It's asking us, man, you were 7 degrees off. Do you really want to move the mount 7 degrees? And I'm saying yes, because what we do in these first couple of discoveries of the night, we're aligning the night sky with the mount's expectation. Again, the mount is this black hardware you see underneath that white RASA telescope. And that black hardware, the whole set of black hardware together is called the mount. It has a set of counterweights that kind of stick out there underneath that you can see down at the bottom. And then the telescope looks through this, see if I can get us back on the telescope. It looks through this red camera through the corrector plate and looks at the sky that you're seeing here on this screen. So now we've synchronized And let's see. I guess this is the cluster. It's not a very pronounced cluster, is it? Let's put our name in here, C1, and we'll go down here also under the title and say C1 and open cluster. And let's open up the information window here. It's NGC 188. So we'll also put that in our title screen down here. Back of the title, NGC 188. You might wonder, well, why are there two names for all of these objects? Well, that's because the New General Catalog was around for 100 years before Sir Patrick Moore came up with this list. Sir Patrick Caldwell Moore, who was an amateur astronomer in the UK, he came up with this list in the late 90s. And the New General Catalog had been around for 100 years. He just collected 109 objects that were scattered across the sky, and he assembled them in his catalog so that amateur astronomers like we are tonight, you and I, would have a good list to work from for a little bit more challenging objects than what we sometimes refer to as the Messier catalog, assembled by Charles Messier. So you can see here the open cluster is like in the middle of this red rectangle, but it's not real pronounced. So let's see if we can find it here. I think we'll do one more plate solve. We're going to do one more plate solve just to make sure, and that'll make sure that we're pointing in exactly the right part of the sky, and so that you and I can have confidence that this is Caldwell 1, the open cluster that Sir Patrick Caldwell Moore wanted us to look at. Ernie's asking, could you talk about how you capture the images? Do you set up a sequence or similar? I think what you mean, Ernie, is, let's see, I'm going to look at our, 0.43 degrees off. So I'm glad we're tuning them out one more time to make sure that we've got this cluster. Now I see it. It's forming up right here in the middle, and we'll see a little bit better picture. We really don't need to do much live stacking because this cluster is already there, but we'll do a little bit just so we can see it a little bit better. So we're going to start the live stack going. So Ernie's asking, well, how do we take pictures of this? We use SharpCap. SharpCap is kind of like a software that controls the camera and then lets us look at what the camera is photographing. And what SharpCap does, it allows you to set your length of exposure. So right now we're using 20-second time exposures, and we have the camera set at about 100 gain. Now gain is a thing that would remind you of on your camera the setting that's sometimes called ISO. It's a kind of a cross between sensitivity and amplification. And in astronomy, gain is more about amplification than it is ISO. But you know, we can think of it that way, and it's kind of the same thing. So in the same way that if you've ever done photography through a single lens reflex camera, you know that we have the amount of time the shutter is open, and also the ISO that you have, the speed of the camera set on. Back in the old days, it was ASA with film, and now in these most recent digital days, it's ISO with the imaging sensor that's inside the camera. Well, we're using an astro-specific camera, and SharpCap talks to it all the way out through fiber optic cable. It goes out and communicates with the camera, very high bandwidth through fiber optic signals. And it gets an image from the camera every 20 seconds. And with every new image, it looks to see in a very sophisticated way what light object is in this frame that didn't change. And because the scope is traveling with the apparent movement of the night sky as the Earth rotates, the stars basically don't change much in the frame. These objects that we're looking at don't change much in the frame. The only thing that changes in the frame are things like the grain in the image. You know, we talk about grain in photography being all the noise in the image. So the light pollution noise, the moon noise, and all that stuff is kind of moving around in the image. So what SharpCap does is it says, okay, my guy wants me to drop out anything that's moving and keep what is sitting still. And sure enough, since the scope, thanks to that iOptron mount, is following the apparent view of the night sky, this SharpCap software is dutifully dropping out all the noise frame by frame. We've taken 8 frames now of 20 seconds each, and you can start to see this picture is looking very, very beautiful here. You can see this cluster here in the middle. It kind of looks like you sprinkled a bunch of salt and pepper, doesn't it, on top of your baked potato. This is Caldwell 1. Now the altitude of Caldwell 1, it's not very high up in the sky right now. What is it? Let's see if we can find its altitude. It's 34 degrees. That's not bad. That's about the height that we would want to start imaging things if we could. What Sir Patrick Caldwell Moore did is he started with the lowest altitude object that he wanted to cover. And then he went up toward, the celestial equator and passed it up and went to the projection of the Earth's equator in the nighttime sky. And then he went past it into the southern hemisphere with his objects, and he went all the way down to objects that we can't even see. And if we're lucky tonight, my friend Michael might stop by from New Zealand. He's actually been working with us to capture some of the objects that only Australia and New Zealand might be able to see, and he's assembling those in a video for us. And then maybe the next time we meet, we're actually going to play his video on this broadcast of the objects that Sir Patrick Moore cataloged that only the southern hemisphere can see. People from places like Australia, New Zealand, South America, the southern half of Africa. And so thank you, Michael. If you watch this in recorded fashion or if you're on listening in, Michael's going to help us out with that. So Sir Patrick Moore made this list, and this is the first object he put on his list. So it's very carefully calculated by altitude. And from his spot in, what was it, Surrey, England, I forget, he was like 50 degrees north. And what are we here? Something like 38 degrees north in Louisville. So this is a beautiful object. It's an open cluster that's a little bit loose. Let's see what they say about it. And C1 is an open cluster, also known as a galactic cluster. Many open clusters have a relatively large angular size, so they are best viewed in binoculars or a low-power telescope eyepiece. Some open clusters are visible with the naked eye, including the 2 most famous, the Pleiades and the Hyades. So not a lot about C1. I would say this is a pretty cluster, but you're looking at it and you're probably thinking, it just looks like a bunch of stars. Right. But we know that these stars are traveling together because we study their spectrum and their spectra. And we can tell by their spectra things about their speed and the origin of their backgrounds, because we can see what the makeup of the stars are. And so we know that this is a cluster of stars that were born together. And now they're moving through space together. Maybe at one time they had some clouds, but they don't anymore. All the nebulosity has long since blown away, and they're moving through the night sky as a group. So that's C1. Let's grab an image of this. And I just looked up there to make sure we indeed had our title. And then let's go over here to our planetarium software. You can see that we looked at this on April 15th also. And on that night we said, nice old open cluster. Not a lot that we said about this. So you see our observing windows open, and we would say, not the most populated group of stars ever, but still pretty. Now we can squeeze a little bit more out of our live stack here. Let's do one more color balance. Let's move our black level over to this crest. And that'll let us pick up a little more of the frequencies of these curves. Once I get it over there by that crest, I can hold down my shift key and then move that bar, and it lets you fine tune it. Move these mids in a little bit. Oh yeah, now we're picking up a little bit more of this cluster, aren't we? Look at all those very, very faint stars that were in this cluster. I'm going to snap another picture because we weren't seeing these before. At 7 minutes, well tuned in the histogram, we could make out a lot more stars in this cluster. Okay, so that's our observation. We've taken our snapshot. Donald's asking what our offset is. You know, Donald, man, my experience with SharpCap, I'm just about a year and a half on and using this. I don't have a big understanding of offset. I'm going to go next target here. Is it over here? Should I be seeing it somewhere? Because I don't know, Donald, that offset really is a big part of my workflow. So educate me. Please help me understand, Donald, if offset should be something that I'm supposed to be tuning here. Now, by offset, if you mean gain, then when I'm live stacking, I drop it down to 100 gain. And we do that because that's kind of a sweet spot for the 2600. So we use 20-second exposures at 100 gain, if that's what you mean by offset. All right, let's go back over here and let's go to C1. And we're going to add that to our list of Caldwell observed. Now it's been put in the observed list, so that means we can come back to our live sky and we can look for Caldwell 1. And I'm making sure that I've got the right object name here, and I do. And I'm going to delete this from our, and I glanced up at the title, make sure I'm in the right list. I sure enough am. We deleted this, and now I'm going to save it. So again, we're removing objects from the working side and pushing them over to the observed side. Now we're going to go back to our list of targets, and we're going to go to C59 next. So we're going to center that in our planetarium software, and we're also going to slew to it with our scope. That's a live view of the scope that you're seeing there. Dan's observing, it looks like your camera is oriented a little bit skewed to the view in the planetarium software. And how are you choosing the camera position? You know, with an equatorial mount, and maybe, Dan, it sounds like you're pretty far along in astronomy. You know that that's a nice view, by the way, of those counterweights. If you look at the mount as it slews there over to Caldwell 59, you can see those counterweights sticking out. The way that an equatorial mount works is that, honestly, the camera position isn't quite, for me, as significant with an equatorial mount as it would be with what's called an alt-azimuth mount, where the altitude and the azimuth are always square on, and your telescope is in a kind of a yoke, and so it's always, you know, moving up and down with what you might think of as straight up and straight down lines in the sky. Then you can set the camera in a place in which you'll always be able to predict how it's looking at the night sky. With an equatorial mount, the camera gets so mixed up because, as you can see right now, the telescope is peer east, but some of the targets will be peer west, and when the telescope changes sides, the mount makes the telescope and the camera look at the part of the sky upside down. So camera position is not really very significant to me. I reached a point after about 3 months that I began realizing, what is the definition of up? Well, in the planetarium software, you can tell what up is. It's toward the zenith. But with the actual camera itself, what does up even mean? I mean, up is a relative word because you can see right now up is almost due east because I'm looking at the same view you're using there, the view of the scope, and I happen to know that this view is from behind the scope, almost as if it would track like a rifle scope, looking up along the rifle scope of the scope if it were pointing at the North Star, almost parallel with the tube, with the optical tube assembly. So right now the up for the mount is actually pretty much east. And another part of the night, up will be west. So it's all relative. And that's why, for me, I just basically don't worry about it. I do orient the camera the same way every time. And that way, I kind of know what to predict in my expectations, you know. The camera is always pointing toward the same spot. And what I use is down on the name of the camera, you know, down on the face of the camera is down on the corrector plate of the scope. So in other words, the camera is oriented with the scope in my world. Dan's also talking about that histogram adjustment. That did help a lot, didn't it? Okay, I'm going to make sure we have our titles in. C59 is our next object. And so I've got it in SharpCap. I'm going to bring up an information screen about this object. And this is a planetary nebula. You know that planetary nebulae are basically the remains of a star that was jettisoning its material into the night sky, so to speak, where the star was. This is C59 NGC 3242. So I'm going to go down to our title here. I'm going to say C59, and then in parentheses, we'll put it in parentheses. How about that? NGC 3242, a planetary nebula. Okay, I'm going to go back up to the screen, and now we're going to look at our screen. See the little dot right there in the middle? We've already plate solved, so I think we're ready to begin our live stacking. And this is where I guess Don was asking a while ago about what was our offset. And he's pointing out to us that gain and offset are two different things. He says, that's okay, I was having problems with SharpCap working for me. He says, I have a different camera. Oh, and Don, you have a QHY, and maybe it does have, when it comes up in SharpCap, maybe the QHY driver does have a separate offset from gain. To be honest, Donald, if there is an offset control for ASI 2600 MC Pro cameras, I've never used it. It's not something that I was trained to use. Donald says, I forgot you're supposed to use a different gain in SharpCap. In Nina, I use gain 0. I will try gain 100 after I'm done imaging MIM 106 with Nina. Yeah, if you're using you said that you're using the same chip. If it's tuned in your QHY like it's tuned in my ZWO ASI2600MC Pro, they have the manufacturer of the 2600MC Pro has it set so that a gain of 100, the dynamic range is the most profound. It's the most number of f-stops, you could say. If you were thinking back in the digital SLR or the old-fashioned single lens reflex camera world, just imagine a lens that had 14 f-stops, and that's what we have at gain 100. Anything other than gain 100, like higher than that, you begin to diminish the dynamic range of the camera, and therefore you're losing a little bit of all of the message that the camera can capture. Yep, Dennis, you're right. It's the Ghost of Jupiter Nebula. And Papa Tech, I'm so sorry. You're in a week-long cloud fest there. That's sad. Glad to see you're only fighting the moon. You bet, Papa Tech. I kind of have this moral... I'm going to click to do a color balance here. Let's take a look at our sky cam and see... Oh my, we're looking square, almost dead on in the direction of the moon. It's a wonder we can see anything, isn't it? So we have to color balance a lot on nights when we have a strong moon, and also we have the sky glow here in Louisville, Kentucky. I'm going to move this, again, I'm going to hold the shift key down. That lets me fine tune this vertical bar in the histogram. There we go. Now I'll take this mid in a little bit, and hopefully that'll let us cheat as much. We're not really cheating, but we're just pushing as much of the colors of the image as we can. Now that's at 100%. You can see that this is a very small target. Let's see how big this is. It says that it's only 40 arc seconds wide. So really, we're pushing the RASA 11, since it's a pretty wide view. We're pushing the RASA 11 in what it can enjoy, aren't we? But at the same time, I think we'll still be able to see this object and enjoy it. It's just not going to be as close as maybe what Hubble would see. Let's cheat in a little more on what we might call our digital zoom. And the digital zoom goes beyond what the optics can bear, and it begins to look inside of this Ghost of Jupiter nebula to see, kind of like a Tootsie Roll Pop, what's on the inside of that material. While that stacks a minute, let's review about a planetary nebula. When a star that's kind of sort of like maybe a red giant, it burns very, very big and bright, but it burns fast. And when it burns through all of its material, it gets a point that it's sort of like a balloon that's withering. And at the last minute, it can't hold that material anymore because it's lost some of its gravity, and because it's beginning to sputter, so to speak, it puffs all of that material, dust and gases, out into its night sky from the star there. And when it puffs it out, now it collapses down and becomes what you might call a white dwarf. And I don't know if we'll see the white dwarf in the middle of this. It doesn't look like we will, especially just stacking 13 frames of 20 seconds each. A grand total integration of 4 minutes. We're not going to see that white dwarf yet. Maybe if we stayed on this object a long time, we would. Let's read in the description. Then what happens is that white dwarf, because it fires back up kind of, it's sort of like a neon light. It lights up all that dust in the sky. So it's kind of like a blowfish, you know, it blows out all that material, and then it lights back up and it lights up the material. So think about a dandelion that would go poof in all directions. And then the dandelion has a firefly that lights on it, and the firefly lights up, and all of those particles from the dandelion now are being backlit by that firefly that's landed on the dandelion. That's kind of what we have going on here. This description, the notes we have here, it says in Starry Night Pro, one of the finest planetary nebulae in the sky, NGC 3242 or Caldwell 59, is a full magnitude brighter than the more famous Ring Nebula M57. A small telescope reveals a pale blue disk. Now we can see a disk, but boy, correct me if I'm wrong, this one, my color blindness is not very good. Looks more greenish to me tonight with the moon maybe. And I am using a filter. It's a Celestron light pollution filter because of the city of Louisville, a Bortle 6 sky. So to us, it looks a little bit greenish. It says that a blue disk with diffused edges. I think we can see those, can't we? And the prominent 11th magnitude central star. Oh, well, maybe it's so big. Maybe it's so big that it takes up that entire inner part of the planetary nebula. I'm used to trying to look for a very small star in there, but it looks like it's so big. Maybe that is the white dwarf. It's a little bit less dwarfish than some planetary nebulae. It says it's about the same size as Jupiter. Wow, that's interesting, isn't it? Hence its popular name. I think that would be the same size as Jupiter in the nighttime sky. So relative to our eyes, it looks the same size as Jupiter. Due to its high surface brightness, the Ghost takes a high magnification quite well, photographs and reveal conspicuous red flyers on both poles of the nebula. Boy, we're not seeing those red flyers yet, are we, after just 7 minutes? These mysterious objects are much younger and move much faster than the gas in the parent nebula. How about that? Photographs. I'll tell you what, let's cheat a little bit. Let's go over here to the Hubble images. Now we're really going to cheat. We're going to go down and find C59 in the list of Hubble images. Yeah, Hubble got just a little bit higher magnification than we did here tonight at Emerald Hills. My goodness, what a unique object. Look at what Hubble found. And here are those red flyers that are kind of bipolar being jettisoned out the side. And here's the size. Oh, there's the white dwarf right in the middle. And then here's all that first layer of material, and then here's that outer layer of material. Almost two different spheres being lit up like a neon light, isn't it? An average star like the sun finishes burning its supply of hydrogen and helium, swells up into a cool red giant star, last gasp before death, throws off the layers of gas into its outer atmosphere in a brief but beautiful cosmic display called a planetary nebula. This exposes the core of the dying star, a dense, hot ball of carbon and oxygen called a white dwarf, which is doomed to fade out completely over time. The white dwarf is so hot that it shines very brightly in ultraviolet light, which then causes the gaseous material expelled by the dying star to glow. Well, so Hubble's Wide Field and Planetary Camera 2 captured this. Caldwell 59, also known as NGC 3242. The ghostly image is part of a collection of Hubble observations made of planetary nebulae in the mid-1990s, which reveal never-before-seen details. Sure enough, we weren't going to be able to see them tonight. It's about 1,400 light years away. Jupiter is only about 40 minutes away, but yet they appear roughly the same size in our nighttime sky. So once again, this is as much as we're going to see tonight with our RASA. You know what? I think we're seeing at 9 minutes, we're seeing a little bit now more of that core, but we're well into our digital zoom. With our optical zoom, we're destined to see only this. So we're going to do our, we did another observation of this. Must have been doing the Caldwell List on April 15th last year. So we're going to come back here and we're going to do a log entry. We're going to say, we loved this tiny 40 angular second. So I don't get this mixed. What that means is, you know how there are 180 degrees in the part of the sky we can see, and then each degree we divide that up into 60 minutes. And then each minute we divide up into 60 seconds. Well, this is 40 seconds of one of those minutes, which is 1 minute of one of those degrees. This is a very tiny object. We love this 40 angular second ghost of Jupiter planetary nebula. We could clearly see the greens after just 10 minutes with lots of white light in the middle, but no red flyers coming out from those poles. Alas, no red flyers. Okay, so we'll close that observation window, take one last look at C59 and bid it goodbye. We're going to stop our live stack and go back to our next targeting level. Let me look down here at the messages that come through. You guys are being very active here. I love this. Mike, Jerry, welcome. Ernie says the default offset for his QHY version of this sensor is for him is 50, but we're pretty sure that for our camera the sweet spot is 100. If you look at the graph, of my camera, there's no mistaking it. It's 100 is the best gain. Mike, thanks for stopping by. Dennis asked how the weather is in the Death Valley Desert. Mike says it's breezy, and it'll be that way for the next few days. Also in northern Colorado, very breezy there. Mike says he used to live in Boulder. He remembers that. Welcome, Michael, from down there in New Zealand. Michael was wanting us to raise the mids a little bit. Boy, Michael, if I raise the mids a lot, it starts flooding the night sky with one of the colors that I don't have quite tuned totally out of my RASA yet. So maybe I'm not able to do that right now on my RASA. Papatech, an offset that is applied to the histogram curve, which offsets it far to the right by some amount, reduces clipping, Very interesting. You guys have to tell me where that adjustment is. Mike Jerry, well, it's pretty similar to Santa Fe. Oh, we're back on the weather. So that would make sense. Mike says offset, brightness, black level refer to the same thing. Okay, so there you go. Different camera manufacturers use the term interchangeably. Mike says the ZWO cameras use brightness as the, and I don't even mess with that because it's kind of, for me, it's kind of futile. Donald, when I'm using the Nina, I use a gain of a 0 and an offset of 30. So that must be with that QHY, or maybe Nina has different controls than SharpCap. Ernie says, no, gain is different. Okay, so you guys have a little bit of, you're going to duke it out there in the comments. We'll let you keep on working with those comments, and we're going to go to the next object here. I'm going to go over here to our planetarium software, and we're going to remember to add this object to the observed list, and then we're going to go back over to the live sky list and look for Caldwell 59 and remove it from the working list and then save. Now you can see our next object is Caldwell 5. And again, these are sorted by altitude right now, not static altitude in the night sky in a perfect celestial sphere. These are rather at Emerald Hill skies, what's the actual altitude above the horizon? And C5 is at 28 degrees right now. So let's open up an info window on the object. You can see it's a spiral galaxy. Let's center it in our planetarium software and kind of see where it's located in the night sky. You see us kind of skating past Gemini, and there's Auriga. We're coming over to this, is this Camelopardalus? So we're looking basically for orientation. We're kind of looking toward the left of Cassiopeia. If you use the more obtuse angle of Cassiopeia to the left there, we're shooting out and jutting right at C5, Caldwell 5. But for orientation, here's the North Star. If you want to make a triangle between Cassiopeia and Polaris, this is where C5 would land. So let's slew to that now. We're going to slew to it. Okay. And you'll see how with our camera now, you remember that a while ago up was to the east. Well, now the telescope is moving its orientation so that now up is going to be a little bit more toward the zenith, and it's going to spin around a little bit so that up is a little bit more in the direction of north now, you'd have to say. So the camera just, it's not worth it to try to figure out which direction the camera is pointing to me. I just kind of live with it and realize this is the curse of having an equatorial mount. Back at the screen, let's go back to our sky. We'll scoot back out to auto here, and we'll do another plate solve. So to plate solve, you can imagine SharpCap has to be talking to the mount and the camera and the software all at the same time, because it snaps a picture, it runs the picture through the software files to find a match of all the starry pinpoints. Then it talks to the mount and says, hey, I'm trying to get the pinpoints in the picture lined up with the pinpoints that you're showing me in the sky. And buddy, you are off. And we were off about a half a degree on this, our third move of the night. Now it'll keep getting better with each plate solve. I'm going to look down here in the comments, and Ernie says the camera has two modes, low gain and high gain. 0 is low gain, 100 is high gain mode. Offset is different from setting from gain. Donald says, Ernie, I know gain and offset is different setting. Ernie says, cool. Mike says, yes, Ernie, offset is different from gain. When using a ZWO camera and SharpCap, gain is controlled by the gain control, and offset is adjusted with the brightness control. So Mike, you're going to have to educate me here because I don't ever use the brightness. So here we are. Let's go back over, and I guess we should be looking at this galaxy, but I'm not seeing it yet. I'm trusting that we're aimed at it, but this is going to be the wonder. Let's take a look real quick at the sky. You can see we're aimed a lot at the Louisville light pollution. See that little band of kind of looks like a sun glow over the trees there? That's That's the Louisville skyline. And we're going to hope to filter some of that out with our live stacking. So we're going to go here to our sequencer and start imaging this. By the way, tip of the hat to Mike. Mike, you were the one who got me started on sequencing. I tried it once, and to be honest, it just was too complicated for me. I didn't like it. It just, to me, I was wrecking everything. And I'll tell you why. I was trying to program too much. And what you helped me do, Mike, is you helped me see, Doug, don't freak out on this. Don't try to tackle too much with your sequence. Just do the basics. So what Mike taught me was the sequencer only really, to be honest, needs to do change your exposure, change your gain, wait a second, start your live stacking, and then clear the live stack. And it's just that simple. So Mike, thanks for getting me started on this. Man, I can't imagine there's going to be a galaxy here. Did I forget to change C5 is what we're on? So thankfully, SharpCap did add the setting. It's going to say, do you want to use C5 for your name when you save? And I do. I'm going to go down here in the title. I'm going to change this to C5, a spiral galaxy. And that is, by the way, NGC. Wow, it doesn't have an NGC number. It only has an IC342. So kind of a weird enigma here. Let's go over to our description. Oh my goodness, there is zero description about C5. This is NGC or IC342. I'm going to go back up here to our browser and say IC342 Caldwell 5 Galaxy, and we're going to see if there's any kind of, oh yeah, IC342, also known as Caldwell 5, is an intermediate spiral in Camelopardalis, located relatively close to the Milky Way. Despite its size and actual brightness, its location behind dusty areas near the galactic equator make it difficult to observe, leading to the nickname, the Hidden Galaxy. No wonder we couldn't see it. It's hidden. Though it can readily be detected even with binoculars. If the galaxy were not obscured, it would be visible to the naked eye. The dust makes it difficult to determine its precise distance. Modern estimates range from 7 million light years to possibly as far away as 11 million. And it was discovered by, not Herschel, William Denning in 1892. It's in a group called the Maffei group, and it's a close galaxy group to us. Edwin Hubble first thought it to be in a local group, but it was later determined not to be. Okay, it's actually wider than the full moon, but smaller than the Andromeda Galaxy. Let me see this thing. I don't think we were seeing it. Okay, so we're going to start some tuning here. We're going to do a color balance. We're going to bring the blacks over to the top of that crest. Again, we're going to hold down our shift key and try to adjust those blacks so that we can be all the way black. Then we're going to bring our mids in. I am not seeing any galaxy. Let's scoot into 100%. Where is the galaxy? Are you sure? No wonder it's hidden. I mean, no wonder we can't see it. It's hidden. We're going to let it percolate there for a minute. We're only at about 3 minutes in the Louisville sky glow on a moonlit night. I'm going to look down here at the comments. Mike says, glad I could teach you something, Doug. You teach me things as well. That's hard to believe, Mike. You've been observing longer than I have. Mike Jerry says, yeah, Michael is right. Your blacks are clipped. Wow, okay, so I'll have to pay closer attention to that. Dennis says, this old Padawan learned something from all of you. Awesome. Mike said, did you plate solve? I think we did. Let's let's stop and replate solve just to make sure. Here we go, next target. And let's plate solve to be sure here one more time. The hidden galaxy is hidden. Drum roll. Brrr. By the way, I will take this opportunity to recommend a book. This is The Caldwell Objects by Stephen James O'Meara. 0.02 degrees. So we did plate solve and we were only 2/100ths of a degree off. But we are correcting those 2/100ths. Boy, how about that? I'm going to go back over here to C5. And I'm just going to check to make sure we are sitting on it. Oh, look. Do you think something was off? It must have made a tiny adjustment. Very interesting. Let's go back here and plate solve one last time. Now that we've got a fresh command to the mount. Anyway, Stephen James O'Meara's book on the Caldwell objects, it takes you through a good introduction of Sir Patrick Caldwell Moore, and then it takes you through a nice, oh my, we're 5/1000ths of a degree on target with this thing. Okay, back to our sequence to launch plate solving. And let's let that be cooking. We'll let that percolate. And so he takes us through one step at a time. So let's go, for instance, all you do is look at these nice big numbers at the top of the page. And let's go to, for instance, Caldwell 5. Mike Jerry says an easy way to find out if you plate solved is to hit the annotate button. If it works, you plate solved. If it doesn't, it'll tell you. Good point. Forgot about that. Michael says, of course, you're very optimistic trying to image a galaxy during full moon at a low elevation facing into the light pollution. Michael, thank you. You might help me preserve some dignity here. All right. So Stephen James O'Meara says, it's a moderately open, clumpy, low surface brightness spiral whose classification suggests a barred galaxy in transition. William Denning first spied the galaxy's sharp central glow and amorphous halo around 1890. Keep in mind, it probably wasn't too bright or else Messier would have seen it. He called it a nebula until Hubble noticed that it had a pinwheel pattern. Oh, so look, it's face on, not edge on. So that'll help us. We're looking for a bright core and some pinwheels. It looks like maybe M74 or M101. Wow, that would be beautiful if it did. Surface brightness is only 15 magnitudes per square arc minute. Yikes. So this is fainter than a 15th magnitude star, because at least a 15th magnitude star has a pinpoint. This takes a 15th magnitude brightness and scatters it out over a square arc minute. Wow. It says its anonymity resulted from its far northern declination, low surface brightness, and isolation. It lies in a plane of dense gas and dust, and it dims the magnitude of the galaxy by another 3 magnitudes. Does that mean it's not worth investigating? No, it's difficult, but you have to be under good conditions to catch it in an 8-inch scope. Yeah, it'll be only under good conditions you can see it an 8-inch. Now we have an 11-inch, but wow, it can be appreciated in a rich field telescope if you have a dark night, very dark sky. You can see it in binoculars, but that's only if you have a very dark sky. When Stephen James O'Meara sketched this, I can tell you the sketch looks like a sketch of dust. So this is not going to be a screamer for us, gang. But, you know, we like challenges. So on a 97% moonlit night, let's see what we can do. Let's zoom in to about 50%. So we kind of get in the right portion of the sky. And we'll set our little scroll bars so we're looking at the right place. Now we'll do a color balance one more time. We're looking at 3 minutes of integration time. We're going to tune our blacks a little better here. Anticipation. I'm going to have to go look that song up on YouTube and play that. Except I'm sure some songwriter would say that I'm stealing his copyright. I don't know whether to push that over here so we can see more blacks, or push it over there so we can see more sky glow. Let's bring it right there. And now let's push these mids up as best we can before we begin to glow the whole sky. Okay, we're going to let that cook a little bit. Magnitude 15 is pretty faint for a full moon night. Mike Jerry says, Papa Tech 15 is faint even without the moon and the city glow. Yeah, you guys are trying to cheer me up here. Man, I'm going to see if I've never observed this before. So I'm going to say here that, well, at first glance, which was 5 minutes with 95% moon and Bortle 6 skies looking toward the downtown sky glow, we couldn't make out a thing yet. Let's go over to our planetarium software and let's take a look at what it's like in it. We're going to zoom in here. I just click on the... Oh, look at that. It's beautiful in our planetarium software. Look at that. That's a beautiful little galaxy. I want to see. Let's see if we can pick out just a couple of these brighter stars from the field of view. Okay, so here's a brighter star out here. So I trust that this is probably one of these out here. Let's go back out to full view. See how I kind of get that sign of a little bit of backspacing left over when I bump those up. And that's just this summer. I'm going to have to tune this up. Oh, here are a couple of noticeable things. Look at that trail of 1, 2, 3, 4. Let me zoom in so you can see that. Look at these. 1, 2, 3, 4, 5, 6 stars in a row. Let's look for that. You know, now that I have zoomed in, I think we might be seeing something here. How big is this object? Only 20 arc minutes. This is tiny. So here in the middle of our screen, Anyway, let's go back over to the planetarium software and look for those 6 straight as an arrow stars pointing at a doublet here. And over to the left is a triangle with two little stars at its top, kind of. Okay, let's see if we can find that pattern. Right here. Oh, there it is. There is the little triangle pattern. Here are the 6 stars. Bam, 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 aimed at those 2 stars. And look at, this is the little triangle that's pointed at those 2 stars at the top of the triangle. So we are definitely pointing at the right object here. Ernie says, that line of stars is a good reference. That's right. Mike says, that little trail of stars is right in front of the galaxy according to the image in Stellarium. Yep, we've all come to the same conclusion. I'm going to center on it again because I hit something a while ago. There we go. Look, those are all Tycho. Those are all named stars. So even when I get in planetarium software, when I get tied in, those little named stars stay with it. It's not an image of the picture that Starry Night Pro Plus put in there. Okay, let's come back here. So we found the location. I'm happy about that. Maybe part of what we're seeing here is the glow of the galaxy. It's hard to admit defeat, but we might have to come back to this because remember the moon is taking away some of the relative searching power, huh? We might have to come back to this on a night when we don't have the full moon. Michael says, must be there. Do you have gradient removal on? Maybe it thinks the galaxy is a gradient. No, I don't think I do. Gradient removal is up here, isn't it? In miscellaneous controls? No. Image controls? No. Pre-processing? Where's gradient removal? It's probably here under background subtraction. Is that the same as gradient removal? There it is to the left-hand side of the peak. Wow, I hope you're right. I'm going to close these little windows that I opened up. And I'm going to search for it. You can see it? Michael, I'm so happy that you can see it. Michael sees it. I'm so glad. I'm not seeing it. Let's zoom in again. When I bump up the mids that high, you're right. You can start to make out the fact that the noise is not all noise. It has a pattern. How about that, Michael? You've got sharp eyes, and that was even over the YouTube live stream. So it's all about integration time, isn't it, for something like this? And I think this shows that electronically assisted astronomy is letting us see something that we would never, ever have begun to hope to see. My goodness, in the light pollution of Louisville, we would have never been able to see this. But I know that if you're an astronomer or a person that's just getting started, you're thinking, you know, I don't see a lot there yet. But it's sort of a pattern of that noise, isn't it? Yeah, Mike Jerry says, I see the core, but that's it. Oh, so you think this is the core? Now I'm tracking with you. That's the core, isn't it? So let's look. Here's the 1, 2, 3, 4, 5, 6 stars. The core should be right in the middle of the 3. And then the core should be accented by 2 stars that are kind of over its head. Let's go back to the planetarium software now. And let's zoom in. Sure enough. 1, 2, 3. There it is centered above that, and these 2 stars right over its head. Wow, you guys have great eyes. See, I think for those of you who are watching this that aren't normally, staring into an eyepiece or working with one of these EAA rigs, I think what you're seeing here is just the experience of some of these guys in the chat stream, the chat box. They're actually seeing stuff that even though I'm right here in front of the very screen, well, to be honest, you're seeing the same screen I am. I mean, I know there's a YouTube loss in the broadcast, but I love it, the fact they saw this core before I did. It shows, again, their experience and also what to look for, So, again, we're just trying to tune this up, and there you can see the way the core does look brighter. There's no way I can tune in very much of the spiral arms yet. I guess it would be like that, wouldn't it? Now this is with 14 minutes, and I would never spend 14 minutes on a normal object. Drag the black point further to the left-hand side. You might see more. Yeah, that's what I was trying a while ago, but it does basically begin attaching grain to the entire night sky, doesn't it? I mean, yeah, I see more, but look, I mean, the whole sky is now toned. So I'm not sure. It's supposed to be a spiral here around this bright core. And I don't know if that is helping. Whereas there, I think it at least allows us to begin to darken the rest of the sky. I guess it's a personal taste thing, isn't it? But that black point does influence it. Okay, we're going to stop there. At least we can say, I'm going to go back into the observation. And I'm going to say, finally, at around 13 minutes, we started seeing at least the core. Still not a lot of spiral structure at 15 minutes. But what do we expect? 15th magnitude spread over a square arc minute. Well, I'm not giving up, but I am. I do think we ought to. Boy, if you use your imagination, you might see something there. But we'll go ahead and save a copy of this. Sky is toned, but the core is now glowing with more material. Yeah, that's right, Michael. Yep, the spiral arms are down in the sky and the moon glowed. Even a really long integration won't pull it out of the murk. Okay. Well, then I don't feel so bad. But it is cool that we can make out the... And keep in mind, in the description here on Starry Night Pro, let's look one more time at the description. That's the description. There is no description. This is the hidden galaxy. All right, so we're going to click this over into add to the observed list, so to speak. We're going to go back here and we're going to search for C5 and remove it and save it. And we're going to make sure that over here, one more time, we're just looking to make sure. You know what? I think we're starting to see an arm. I think this is an arm. I'm going to name it and claim it. Maybe. I don't know. Of course, now I'm at 500% digital zoom. You know what? I think it is starting to form up there, isn't it, guys? Look at that. You can see a lot more of that circular noise pattern now, which tells us that it does have a pattern. Okay, Dennis, thanks for being with us. Oh, you got to go do the dishes. Keep Mama happy. Michael, thanks for stopping in from New Zealand. This is why astronomers work on DSOs wait for dark of the moon. Yeah, Mike, Jerry, I'm afraid you're right. Okay, that's it. We're going to move on. I think it does show us the advantage of having a dark sky, but I'm happy at least we saw the core. Next object is C45. And we're going to center it and see where it is in the night sky. This one's getting lower. 17 degrees. I hope we can still see it. I think my trees over there are at 15. We're going to slew there. And remember, the only reason our telescope can see over the top of the walls of this observatory is because of that height adjustable pier. There's no way that we could have had a telescope this high up to be able to see above the wall of the observatory. There's just no way. Let's use the sky cam, and that wall that you see in the lower part of your frame, that is the wall of the observatory. It's a roll-off roof observatory, and you're looking over that wall. You see, basically, if you can look at where this is the very direction of the sky that we're looking in, and you can see how the scope is just barely up at the axis, is level with the top of the wall. And that's because of that height adjustable pier. And when we get ready to roll that roof back on the observatory, we lower that height adjustable pier down about, 40 inches or something. And then it's inside the observatory for that roll-off roof to close. So, it's really a neat concept, isn't it? And it does allow us to be able to look over the edge of this wall. So let's see what we can do here. Let's see. So we're at C46, and we're going to slew there now. Oh, we already did, didn't we? So let's go back here and do our plate solve. And of course, we're thankful for the SkyCam. The SkyCam is the little red monochrome ASI178, which is mounted on top of this little outrigger device. We were about 0.6 degrees off on our slew, so it's correcting that. The blue boxes, the one on top is the Pegasus-Astro Powerbox Micro. The one underneath is the Pegasus-Astro USB hub. And those basically pull together the signals from the two cameras and make them one. They also pull together the signal from the power box so we can get the metrics of the night sky in the box there. Okay, let's start. We're going to change to C46 here and start live stacking. So we're going to go start imaging. And then down here in the title, we're going to say C46. And C46, Caldwell 46, is Hubble's Variable Nebula. How about that? It's a diffuse nebula. And it's also known as NGC 2261. So in our title, we'll say NGC 2261, a diffuse nebula. Okay. So now let's do a color balance for this part of the night sky. Let's bring our mids over. And, oh yeah, we're going to see Hubble's Variable Nebula here. We're at 135. Let's get us back to 100 degrees. So that's the full resolution of the camera. Let's back off the mids just a bit and darken the sky just a little bit so it stands out against a darker sky. Look at that. Boy, that's a cool object, isn't it? It almost looks like a comet. I guess Messier, if he had a better telescope, and what's the altitude of this right now? It looks like it's at 16 degrees. What's the position in the sky? This is at an azimuth of 268 and an altitude of 15 degrees. I guess this would have probably been pretty low for Messier from his vantage point in Paris, huh? Ernie says, so are you slewing your target with SharpCap or with the planetarium software? Sorry for the SharpCap questions. I use Nina. Mike answered, he's invoking the slews with Starry Night Pro, but SharpCap can also control the scope, which is how it plate solves and syncs. And thanks, Mike, for covering that question. It's like teamwork here, huh? This is a neat little object. We're at just 120 seconds, and we can already see this. It says it's a diffuse nebula. That's about all that it says. Not a lot specifically about this particular nebula in the Starry Night Pro notes. Let's see what we can find if we go out to NGC 2261 out here and say NGC 2261. It's a variable nebula. Why is a nebula variable? It was discovered by William Herschel. He imaged it at Palomar for the first time in 1949. Oh, wait. Herschel discovered it in 1783. Palomar imaged it in 1949. Hubble had studied the nebula previously at Yerkes and Mount Wilson. Hale had taken photographic plates with a 24-inch reflector in 1916, and using all those different images with a blink comparator, they were able to detect that the image changes it changes brightness. And would you say that a reason why a nebula might change brightness is if it's illuminated by a star which is changing brightness? And in this case, the star is R Monocerotis, which, by the way, is not directly visible. And so it's it's being lit up by a star that we can't see, which must be a variable star. It's near the Cone Christmas tree cluster, a winter target. How interesting is that? And we're seeing it here now in the spring, right on the horizon, because we're doing the Caldwell Catalogue. It's beautiful, isn't it? It's really a cool little thing. It looks exactly like a comet with a wide tail. So we're going to go over here, and we've never observed this before. We're going to say Caldwell 46 looked in our screen like a comet with a wide and diffuse tail. We could see the bright core, the head of the comet, so to speak, and the coma faded from, what would that be, a yellowish green. You know, I'm tempted to zoom in on this with what you might say is digital zoom. So we're at 183%. Just because you can see the shape of it at least now still, with that bright head of the comet there, and then this tail kind of streaming behind it. But it's not a comet, it's a nebula. Curtis Horn, how are you, man? We're looking at C46, Curtis, and it's looking a lot like a comet in our night sky. Here's our sky, Curtis, and we're trying to dig this comet out of that Louisville brightness. That's not even the main part of the Louisville brightness, but there is some southern part of the sky there, and that's the scope we're using, Curtis. And there's our view. So this is a lot of fun. Thanks for spending these moments with us, guys. Let's image this. Save an image of it exactly as seen. And then let's head on to the next target. This is Hubble's Variable Nebula. How about that? C46 in the Caldwell List. And we're going to say observed, and then we're going to go back over to live sky, search for 46 and remove it from the working list and save the working list. Come back here and go to C54. Let me do another altitude sort here. Well, we haven't gone to C6, which is actually higher now in the sky. Let's go to C6 next. So we're going to center it. See where it is, crossing Gemini, crossing Auriga, moving past Camelopardalis. We're going to go into Draco. So now let's slew there and let you watch that journey. It's basically a pure, a pure 180, a Meridian Flip, you might say. Curtis says, Caldwell List, my favorite list. That's awesome. You must love these faint targets. You like a challenge, don't you, Curtis? I was thinking when I was listening to a recording of another amateur the other day, kind of dreading a Meridian Flip. I got to tell you, I don't even care. I don't even notice things like Meridian Flips because this mount is so dependable and it never complains. It just zip, 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 just goes from one side of the night sky to the next. So I'm just glad we don't have to worry about that thing. Meridian Flip is when it changes from the west side to the east side of the sky. And Meridian Flips, I guess, if the mirror messes up on your scope, or if the mount gets out of adjustment, or if the scope is kind of loose, loosely mounted or something, I guess it would be a little more fearful. But by God's grace, with the rig that we have, we don't have to worry about Meridian Flips. We're doing a plate solve now to catch this. It was just 0.34, so 34 hundredths of a degree off after that meridian change. You can see the little, no you can't. There you can see a little repositioning, stars kind of still settling in. And we're at 3-second exposures here at gain 400. So let's change our name to C6. C6 as opposed to C4. And then let's start our sequencer here to start image. And let's go down to the title and change it to C6, which is also called, drum roll, NGC 6543. C6 is NGC 6543, a planetary nebula. And this particular planetary nebula is called Cat's Eye. That's fun. We love these nicknames, don't we? Kind of, you know, gives you something other than a phone number for an object. You know, we can see something right there in the center that is not quite as much of a point of light. Let's do a color balance since we're in a different part of the sky. Move our dark black level over there and move our mids in, and then jump to 100%, and right there we are, the cat's eye. Boy, it's pretty tiny. I'm gonna have to use some digital zoom here to give you guys a bit more view of the cat's eye. We're at 80 seconds though, so boy, it looks like I've looked at this before. On August 3rd of 2021, I wrote, we imaged this at 20 seconds at 300 gain, and it was blown out. Back down to 30 seconds at 100 gain, we could at least see some color. On March 27th of 2021, we wrote, attempted to observe, but not really sure I ever truly saw it. Appeared like an oval star, not much hollow in the middle. Very tiny. And then February 19th of 2022, it really does look like a cat's eye. So tonight we're going to say, still just looks like a tiny cat's eye. Not much going on in the middle at 2 minutes exposure. We're at 195%. Oh, I'm so sorry. Just to have you guys on the black screen. Thank you, Mike. Sorry. Thanks, Curtis. Thanks, Ernie. Sorry. I was editing that title. And when you edit the title, you have to run down there real quick. So here we are. Let's go over to the planetarium software and look at how tiny it is here. So that's the frame approximately of a RASA 11, and you can see how the star points and this planetary nebula are about the same. But boy, when we zero in, oh, that's exactly what we're seeing. How about that? We're seeing exactly the same thing. Let me fix it here so we can look at both at the same time. Oh, it's exactly the same. That's funny. Yeah, I'd say we're starting to see a little bit more green. Like I said a while ago, we are running the Celestron light pollution filter that's designed for the RASA 11. So, you know, and the moon is 94% or 95%. So I'm not sure what color we should be seeing because this color is not very strong, is it? In this view that we're seeing here in the planetarium software, it's mostly all just a white glow with maybe a slightly greenish, orangish, yellowish tinge in the middle, but not much, huh? And we're not sure if this star is the core star or if that's a star that lies between us. I bet it just lies between us. So back at the real thing now, let's save a 4-minute image of this. And that's the Cat's Eye Nebula. So, when you think about Sir Patrick Caldwell Moore, let's take just one split second and compare. How does his list compare with the Messier list? Well, remember, to be fair, Messier was actually a comet hunter. He dealt with stuff that was in our solar system. He wasn't interested in interstellar space, deep space objects. He was looking for things that were in our solar system, comets. So his list tended to be stuff that was in his way, and he just mainly cataloged it so he'd be able to look over there and say, oh, wait, don't waste your time on that, Charles. He was trying to get it out of his way. And so his list, the Messier list, we've come to call it, it's 110 objects that are spectacularly more visible for the most part to beginners and to all of us, not just beginners. They're bigger, they're brighter, and for the most part, most of the time, a little more spectacular than these smaller, harder to image objects that Sir Patrick found for us in the late 90s with his better gear, and his 300 years extra experience since the top of that Paris hotel where Charles Messier was observing in brightly lit Paris. So what Sir Patrick Caldwell Moore did, he listed the objects in the order of altitude, starting in the north sky, and he travels all the way down to the south sky. And you saw Michael a while ago from New Zealand. He's preparing a video for us of the Caldwell objects in the southern sky that we can't see up here. And next observation time, hopefully his video will be done by then, but in one or two of the next ones, we'll look at that video, and it'll probably be 30 minutes long, all of the southern sky objects. So we're looking forward to that when he gets that done. All right, one more tune-up. Hold the shift key down and fine-tune the blacks till we can get as much color as we can out of this. My color perception isn't much. Do you guys see much color in this? I'm not seeing a lot. Okay, anyway, that's Caldwell 6. The Cat's Eye. One last time, let you see that. There's the Cat's Eye. And I'm just going to say here at 7 minutes, it's still I got that thing going on where we're going to have to delete this log entry and do a new one. But I still looked like a cat's eye. I've shared that bug with SimCur and asked them, can you guys please fix this? They have not fixed it yet, but I know they will before it's over, so let's have faith. We're going to add that to Caldwell Observed, and then we're going to go over to Live Sky and find C6 and delete it from the working list and save. And let's do another altitude sort. Looks like 60 would be the next at 33 degrees. We're going to center on that. See you now. Okay, back to shortcut. Yeah. So now the planetarium software, this is not our live view, of course, obviously, because you can see constellations on the night sky. So you knew it wasn't the live view. The planetarium software is headed over toward the south. Now that little line in the sky is the south meridian. So we're going to have to do a meridian flip, and right there is a cool looking object. 2 little interacting spiral galaxies. Wow, this is a fun one. And so this is C60. So let's now slew there. And it's also fun to look at this in the sky cam because you can sort of see the scope in 3-second increments. You can see it working its way around through the night sky. So, you know, this observatory is really fun. It just takes about, you know, I don't know if it takes 5 minutes or 7 minutes to open everything up now. It's so fun. The telescope, I just take a lens cap off of it. You could call it a lens cap. And take a lens cap off the this little 178 camera, you know, the little monochrome camera. And just go to this rig rack and hit a power switch over here to the right-hand side of that rig rack. And it powers everything up. Come back to the mount, hit a power switch on the mount, and it's ready. And that's all there is to it. So it's really a lot of fun now to be able to launch this thing. Next target. To be able to launch this thing in 5 minutes or less, it's really a lot of fun. So, okay, so here we are. Let's go back to full view, and this is what was it? 60. Was it C60? Now I forget. And yeah, C60. C60. Let's open up that info box. And looks like we imaged this April 15th in 2021. We liked when we zoomed in, seeing all the material being pulled apart by the tidal forces. So this is C60, and that already plate solved, didn't it? Let's use Mike's hint. We're gonna look at the deep sky annotation, and we haven't plate solved yet. So I'm going to take that off, and now we'll plate solve. Ernie, thanks for visiting with us. We appreciate you being here. Good luck there in northern Colorado. So we were here about we were a little bit off, weren't we? 0.82 degrees, so a little over an 0.8 of a degree. And I'm sure that's just because we traveled all the way around, did that flip, came to the back of the night sky. There's still quite a few people on the live stream. If you guys have not told us yet where you're watching from, your vantage point, we'd love to see that. If you haven't checked in, it's a lot of fun to kind of see what your particular vantage point is. Okay, so let's start our imaging sequence. And again, this is C60. So let's go back down to our title here. And this time I'll try to remember to go back to the screen after it. NGC, wow, 4038. And this is a spiral galaxy. Let's say an interacting pair of galaxies. How about that? screen. Won't forget this time. Okay, let's close this and do a color balance. You have to get one frame in for color balance. Doesn't hurt to have two. And then we use the peak color balancing method to color balance based on the peaks in the couple of frames. You can see our object starting to form up there. We'll jump into the 100% zoom of the optical zoom. And London, UK. Corin, nice to have you with us. So if you're in UK, that means you got up early for this. It's probably just what? Is it 5:20 a.m. there? Corin, what gets you up so early? Simon from Perth. Sat here eating lunch, enjoying your live stream as usual. Simon, that's so kind of you. Thanks for logging on. You're a good friend. Corin, I'm trying to figure out why you're up at 5:20. Please fill us in. This galaxy is already forming up after just 100 seconds. And keep in mind, that's what we're looking into. That's a live view using this. See that little red camera on the front of the scope that's on that little outrigger equipment plate? This is a little red camera's view. And look at where we're staring right into a 95% moon, but using the magic of electronically assisted astronomy, we're at least able to see this. It's not the most beautiful view yet, but we can at least make it out. Let's go over under the description. NGC 4038 and 4039 together form the ringtail galaxy, or the antennae, an interacting pair of barred spiral galaxies in Corvus, which I think, doesn't that stand for the crow? 70 million light years from the sun. Wow, that always gets to me. The live view that you're seeing over here, this live view left these two interacting galaxies who were in a bit of a cat fight some 70 million years ago. And although we would like to referee this cat fight, we don't know who's going to win, do we? Because this battle that's going on here, we're seeing the 70 million year ago version of it. Look at these these look like stars that were formed in those two interacting galaxies. Here you can start seeing this bar of this barred spiral. They've spawned intense star formation in both galaxies. So let's start a log entry here and say, even after just 3 minutes, we could already make out the bar in which side is that? Let's go back to our planetarium software and zoom in a bit. So 4039, and this other one must be 4038, isn't it? 4039, yeah, 4038. So 4039 is the one on the left. We could see the bar on the right. See the bar there. 40 in NGC 40. Oh, which was it again? 4038. Wow. It's amazing that we can see this. What is the angular size of this? Only 5 arc minutes. This is very, very small. Kim, just tuned in from Adelaide. Welcome. Corwin, I just woke up. I saw your live EAA YouTube last 2 weeks also. Oh, last 2 weeks ago. Very enjoyable to watch you guys imaging from all over the world. Wow, Corwin, that's very kind of you to join us. Honestly, it makes us feel like a team with you when you join us in this. So I think this is a better view of the antennae galaxies. We could really see the antennae formation a lot better, this observation. All right, one more time, a little bit of digital zoom so you can see a little bit close in on those structures. And we could try to push these mids a little more, couldn't we? Maybe see a little bit more of that star formation going on, although it causes the night sky to go berserk with all the moonlight. Let's save this. One other thing I want to talk about, I'll do a video on this, 5:23 a.m. Core, and thanks for being willing to join us. If you are a Starry Night Pro user, I just want to say that there was no Caldwell List at all in the choices. And this is C60. I guess we somehow see Caldwell working. And it's trying to sort out now which ones are visible. And then we'll sort by altitude. And there's C60 at the top. We're going to add that to the Caldwell observed lists. And then we're going to go over here in live sky. And we're going to take C60 out of the list. So now we have a clear count or a clear list of the objects that are still yet to observe and the ones we've already observed. But I just want to say that in Starry Night Pro, there was not a Caldwell list. So I had to make one. And you know, to make these, you go up here under Observe, and then you go to Observing Lists. And you can pick out like a bunch of different kinds. You can even say from list, and it goes out to the web and finds the current lists that people have uploaded. Like here are the ones from the Texas Star Party. Here are the the Astronomy League, Astronomical League observing stellar evolution. Here's the Astronomical League lists. Sioux French Deep Sky Wonders. And any of these observing lists you can download. Well, guess what? I could not find a Caldwell list at all. No place. So I finally just decided, okay, I'm going to make one. You know, it wasn't that hard to start it, but what I noticed right away, and now I know we're in our closing minutes, I want to mention this. What I noticed right away is that in Starry Night Pro, you couldn't search by the Caldwell numbers. For some reason, it doesn't let you. You can only search by like NGC and other catalogs. So Starry Night Pro started in the late 90s. I bet the Caldwell list was not very popular, and I bet nobody's added it since it opened. You know, Starry Night Pro released. So there was no Caldwell list from which I could base a list. So I just assembled it one object at a time by making a new list and then adding one object at a time. But because you weren't able to search by Caldwell, you had to add them as NGC lists, and they stayed NGC lists. So last observation, you might remember I was having to search by NGC list. But this past weekend, by God's grace, I figured out how to go into the observation list in the JSON files and edit the JSON files so I could change the name to be able to make this Caldwell list with the Caldwell numbers in all but the Coalsack Nebula or whatever it's called, which I think is Caldwell 99. And for some reason, I could never get Caldwell 99 to work, so I just had to name it Coalsack. But in all the others, I got the JSON file to rework and then save this. Now I need to upload it somehow to Starry Night Pro, but I don't know how to do that. Now, it did correspond and come into live sky, we have the observing lists here, and it is the Caldwell list that I made. It's here. So here are all the objects I typed in and changed the name in the JSON list by hand to the C Caldwell number. Notice how it shows you a preview of them. So I really love being able to edit the code of the JSON code. I had no idea what I was doing, but it was fun learning how to do it. So I'm going to make a video about that for you guys who are using Starry Night Pro. Well, that about wraps it up. It is 12:30. Azray, thanks for checking in. We've had a good time tonight, even though our time is gone. We've worked in the Caldwell list, and I'm gonna search here in the lists. I guess I still have to search for something else first. Now I'll search for lists again, because what I wanted to show you is the observed. Here are the Caldwell objects that we've observed so far. And I think we can put them in name order like this. So 1, 3, 5, 6, 7, and so on up to 60. And we're going to keep on working through them. The ones that are checked are the ones that we've observed tonight. So we did 7 objects tonight. And we're going to keep up on our game so we can do more and more objects. I think we slowed down quite a bit on the hidden galaxy. That we spent quite a bit of time on the hidden galaxy, didn't we? But we'll keep on up on our game and we'll work our way through. Looks like roughly, what would that be? We can count them here. If we go to observed, oh, here we can get a count of them, can't we? Can't we? Yes. If we go back to observing lists, we can see instantly that the observed list is 22 objects. So we're 22 objects along on our list of 109 Caldwell objects in our series. Thanks for joining us tonight. Again, we've come to you from the outskirts of Louisville here at Emerald Hills. I want to thank you for being with us. If you like this kind of content, please hit subscribe. If you don't mind, it's not that expensive, I hope. Click the thumbs up. In other words, it doesn't cost you anything. And if you want, click the bell, and that way you'll be notified when we do content like this. That gets it up at everybody else's heads-up displays in their YouTube browsing. So that'd be a great help if you don't mind. And we do basically most weeks the clearest night and the second clearest night, at least a couple of observations per week. So I hope you'll stop back by. And one more time, I want to thank God for making all these objects and putting them there in the sky and allowing us to be able to zoom in on them. We'll look forward to seeing you next time. Until then, we'll just say for tonight, good night and God bless you from Emerald Hill Skies. That's it for this evening. Goodbye.